Most of the information that codes for eukaryote life is encoded within DNA. We have dozens of trillions of cells inside our body, and each of these contains the exact same DNA. Copies are very expensive to make, and they must be made every time a cell replicates. DNA is also very expensive to maintain, since it often suffers some form of injury, which the cell's internal mechanisms must repair. This is done at great energy cost to the cell itself. So, why do we have DNA in every single cell of our body, instead of only having one or a few cells that hold this DNA? The answer to this question is a very good example of distribution, redundancy, and concurrency in action. First, to answer this question, we must look at a simplified example of how DNA works. It boils down to this. There's a complex biomolecular mechanism that transcribes a sequence of DNA into messenger RNA. There's another complex biomolecular apparatus centered around the ribosome that translates this RNA into a polypeptide, which will later fold into a protein. This process is somewhat straightforward if every cell contains a copy of the DNA. But assume for a second that we could create or evolve an organism that only has DNA in a few memory cells, designated to hold genetic material. On the surface, this seems like a rather good idea. As mentioned before, it would save the organism a lot of energy, seeing as it no longer needs to maintain and replicate DNA within each cell. However, a few issues will arise from this approach to multicellular life. First, there's a sort of transport overhead. Now that we only have one out of many cells holding DNA, other cells must send it a form of request in order to get from it either a molecule of RNA or a protein. This would involve a complex signaling mechanism to determine what cell requested what and guide that protein or molecule of RNA back to the cell. It would also involve transport overhead in the form of a protective membrane around said protein or RNA to help it safely arrive to the cell. Lastly, it would involve overhead in the form of the time that it takes for the cell to receive the payload it requested from the memory cell. Then there's the issue of queuing up to read a specific DNA sequence. Unlike a database, the data from a specific part of our DNA cannot be read in parallel. Each reading of a particular sequence makes it inaccessible until the read is finished. In that sense, reading from DNA is much more similar to an update operation than a read operation. This means that if a lot of cells desire to create the same protein at about the same time, a reading queue will form for the sequence inside the memory cell. Adding to this design, not only the transport overhead, but also a possibility to wait a long time until the reading operation can be finished. Third, there is the issue of mutation. DNA can get damaged for a variety of reasons, and our cells have internal mechanisms to repair this damage. But assuming those fail, our immune system is also present in order to destroy the damaged cells. With a centralized design, this becomes much harder, since a single cell gone bad might affect many other nearby cells in a very short duration. Thus, whilst damage would happen less often, once it happened, it would be much harder to actually recover from it. This example is obviously a bit simplistic, and I don't claim that these are the only reasons or the main reasons why a centralized design in terms of DNA storage hasn't won an evolutionary race. But I think that this model might shed some light on the importance of distributed information. That being said, I think we should move to a more familiar territory of databases and data processing code. I want to look at three facets of using multiple hardware or software entities for the same task. People often confuse these in terms of what they do, and more importantly, they are confused about which of them are required for a specific problem. Those facets are concurrency, distribution, and redundancy, and we'll start with the former. Let's assume that we are in a situation where we have a bunch of data sources sending us events. We have a data processing task that processes these events independent of each other and places them into a file and stores that somewhere. This is the kind of task which we can easily make concurrent. It scales with almost no overhead. All we need are more entities that can run a similar data processing task, and we can suddenly make the process much faster ad infinitum. This means that if we are getting too many events to process, instead of making our code or the underlying hardware more efficient, we can simply use more of the same hardware to run more of the same code. A very easy solution to an otherwise potentially hard problem. Of course, in this ideal case, each of the events coming from the data source is processed individually. In a less ideal example, we might have to take into account things such as the ordering of events. Let's assume our data processing task must feed the processed events into a time series processing task. This requires batches of 6 consecutive events, let's say. And this brings in the need for a synchronization mechanism. Even if the data sources sends the events in order, there is no guarantee that our parallel processing tasks will finish processing them in order. In this case, we'll need a buffering mechanism to help us synchronize the events from these various processing tasks. This mechanism will simply create memory buffers for pairs of 6 events. Wait until a buffer is filled, then send it to the time series processing task. A rather simple synchronization mechanism, but it adds some overhead by virtue of having to store each buffer until it gets filled up, having to determine what event goes into what buffer, and when to send a buffer to the next step. Even worse, we cannot really scale this synchronization mechanism, and this will become the Achilles heel of most concurrent systems, their synchronization mechanisms. Next, let's look at the concept of redundancy. Let's say you've got some API running on top of some server, processing data from some store and sending it to a variety of users that request it. Assuming this machine's running your API breaks, all your users will be left without their data. Assuming your API is a critical component of some system, this could be a catastrophic occurrence. In this kind of scenario, we need a redundant system. In this case, a redundant system might involve running multiple copies of your API and some sort of routing service, which in itself must be redundant or very resistant in some way. And assuming one of your servers once again breaks, the users are simply routed to an identical copy of the API, noticing nothing except for a slight downtime in their requests. The more servers you have, the safer the system becomes. Redundancy is also what we'd call something like storing multiple copies of the same data in case one of them gets corrupted. Essentially, a redundant system is one that has fallbacks. There is no single point of failure within it. Obviously, what that means depends on the kind of system you are working with. In the end, most systems do end up having a single point of failure, but by making certain that key points of your system, which also happen to fail often, are redundant, we can nevertheless reduce the risk of an outage. Another thing that you may notice with this redundant system is that while all your servers are healthy, you could split the requests among them, thus reducing workload on individual servers and possibly increasing overall speed. A lot of redundant systems often lend themselves well to also being concurrent, and vice versa. Yet the two concepts shouldn't be confused, and you should always keep in mind what you are aiming for. That is to say, if you are aiming for concurrency or if you are aiming for redundancy. Otherwise, you might well end up over-engineering your solution. Lastly, we'll analyze the slightly more complex concept of distribution. Let's look at an example where we not only need to distribute workload, but we also need to distribute data. Let's say you have a very large data set of customers' data. Let's also assume that this data is indexed by week. For any given week, we have a bunch of files, and usually our queries will filter by this week value. We could store this huge data set into multiple databases sitting on separate servers and use the week value as the distribution index. Thus, we are left with a separate database for each week. This is helpful because it allows us to actually store a large amount of information that might not fit on a single machine. However, this is not only data that we can distribute amongst these machines, but also the workload on said data. If your distributed database is worth its salt, it probably has a program that will distribute certain queries amongst the databases. Let's look at a specific example here. Let's say we want to select all the actions of customers from week 1 or 2, where the action is of a specific type only if the customer's ID is present in the dataset of week 3 as well. We can split this query into 3 individual queries, running on all 3 databases concurrently. Finally, once all the queries are executed, we can merge the datasets in order to get back our initial query, which we must then finish running on a single machine. But it'll likely be much faster because the size of the data on which it has to run is quite small. Often enough, as in this example, if we distribute our data, we can also distribute the workload on said data. And in a situation where we must distribute our workload, we must usually find a way to also distribute the data in order for it to be efficient. Alright, let's look at all these concepts together in the example of a CDN, a content distribution network. Let's start simple and say that you have a server with a bunch of images somewhere in California. And you have a bunch of users also in California. Thus, when they access the URL to one of your images, a DNS server points them towards your California server and the user quickly downloads the image. All well and good, but what if we introduce users from France or Japan? They go through the exact same process, but due to them being far away from your server physically, the bandwidth with which they will download the images will be rather abhorrent. The solution to this is a CDN, a content distribution network that replicates your images amongst multiple servers and distributes the requests among these servers based on their proximity to the user. This is an example of workload distribution that falls under concurrency, distributing a task but replicating all the data amongst all the entities. In this case, concurrency not only makes the task faster by adding more processing power, but it also makes it faster by allowing the users to access an entity which is best suited for their needs, in this case a server which is closest to them. Furthermore, this system is obviously redundant due to the data replication. If one of the server goes down, we can simply reroute the user's requests to the closest server which is still operating. But we can also use this system to distribute data. Let's assume we monitor the specific images that users from various countries tend to request most. If we observe a specific pattern here, we can decide that instead of replicating data on all of the servers, we need only replicate the data on the servers where said data gets requested very often. If a user happens to request an image not hosted in his region, the distributed nature of the system simply means that he has to wait longer until his request is finished. Thus, we can see how a CDN makes use of all of the concepts we have discussed. Its data is redundant by nature of being hosted on more than one machine. Its data can be distributed if we decide to split the data between machines rather than having all of the data on all of the machines. And its workload is concurrent, since it can be executed by any one of the servers and multiple servers can execute their tasks at the same time. Finally, I would like to make some observations in regards to a few inconsistencies in this video. First, if you are slightly confused about the differences between a distributed workload and a concurrent workload, that is understandable, since the two definitions often overlap. The two main differences are A. Work can be distributed amongst multiple machines even if it's not done concurrently. That is to say, each machine can be doing a specific task, and some of the machines might have to wait for the other machines to finish before they can begin their work. So work can be distributed even if it's not parallelized, though in reality this will seldom be the case. B is more of a semantic definition. Generally speaking, when we say we are doing a task concurrently, we often refer to doing the exact same task on multiple machines or threads, as was the case in the data processing example. When we say that a task is distributed, we often refer to splitting a task into multiple smaller tasks and running them in parallel. In theory, both of these would be considered concurrent, but in practice, people often talk about the former as concurrency and the latter as distribution. Second, in the CDN example, when we decided to distribute our data, the drawings show that it was the DNS that routed our request to another server when a particular image wasn't present on one of the servers. This is not how the system would actually work. Actually, it would be the server itself that does the rerouting once it cannot find the image locally. However, I noticed this once the video was already done and I couldn't find the original drawing to modify it, and I thought that it doesn't really change the point of the video much, so I left it that way. Last, I would like to quickly address possible concerns with the lack of code in episodes 2 and 3. Essentially, I did intend to have code examples in episode 3, but it would have made the video too long. Instead, I've decided upon creating a separate episode that addresses writing concurrent and distributed code, which will probably be the next episode in this series, and I'm hoping to release it sometime in June. Also, if you have enjoyed this series thus far, I would appreciate any help in promoting it on Twitter, Reddit, LinkedIn, etc. These videos are not monetized or sponsored, so I have no financial incentives here, but as a creator and an author, I am always thrilled when people watch or read the things that I put out, and I try to spread the word as best I can. I also strongly encourage you to email me with feedback on how I can improve the videos and what kind of subject you would like addressed in the future. I try to read all emails I get from people reading or watching my content, and I do take them into consideration.